Good afternoon, everyone, and thank you for being here. So today, I'm going to talk about our journey in support of Protobuf in Uber's streaming processing platform. So unfortunately, my colleague, Shaz, who is one of the main contributors of this project, is not able to be here today. As for myself, my name is Yang, and I'm a software engineer at Uber. And my team and I are working on building a reliable and scalable Kafka and Flink platform as a service for engineers at Uber. So this is today's agenda. First, we are going to go over some high-level information about streaming processing platform at Uber, a few key components, and then we will discuss the motivation of our projects, followed by the architecture deep dive. Then we will wrap up our talk with learnings and next steps. So I guess I don't need to say what Uber is, right? Everyone should know. But as many of you know, Uber's business is real-time by nature. So when a rider requests a ride, they want to get on the road as soon as possible. And also, as drivers, they want to take as many rides as they can to maximize their time and earning. And the real-time data platform plays a really crucial role in Uber's overall architecture. And the streaming processing platform is one of the very important part of Uber's real-time data platform. So next, let's take a look at the key components of Uber's real-time data platform and also deep dive into the streaming processing platform. Real-time data platform at Uber includes three main components. Streaming data is built off Apache Kafka. You all know what Kafka is. And the streaming processing platform built on top of Apache Flink. The real-time analytics platform built on top of Apache Pinot. They all considered as the critical infrastructure at Uber and being used in various of the Uber call trip flow. I listed the data lake ingestion here, which usually considered as a batch processing, but it's still a very, very important part of the data stacks, so we cannot miss it. So as shown in this diagram, the streaming processing platform plays a very crucial role of the overall real-time data stack. It is responsible for filtering, transforming, enriching the data, doing the computation. And often, this data gets pumped into Kafka back or goes into other data stores, then being used in the real-time applications. So we have a variety of use cases for Uber's streaming processing platform, including real-time notification, the monitoring, alerting, fraud detection, and also more. We are also recently exploring to use Flink for the data lake ingestion, which will further expand the Flink's use case at Uber. So overall, this is a self-service platform. Users can create jobs through self-service UI, and us as a platform team do not need to get involved. So we offer two different Flink solutions. A Java-based microservice solution, which allows users to fully utilize the powerful streaming analytics capability of Flink. And also a SQL-based Flink solution that makes write Flink SQL as simple as just write a SQL query. In terms of scale, the platform provides 49 SLA for critical jobs. It processes around 6.5 petabytes of data per day, and we have around 4,000 jobs running across multiple regions. The end-to-end latency is in terms of seconds. OK, as I mentioned before, we have two different options for users. A Java microservice-based solution, typically more suitable for more advanced users or data engineers. So it allows people to fully utilize the powerful streaming analytics capability of Flink. The platform provides the common connectors for convenience. And the entire development flow is very similarly to developing a microservice. Well, we have another platform called AthenaX, which is a Flink SQL platform. So it is a fully managed platform. So like my team is managing this. And like for users for this platform, everything is operated through a UI. So they don't need to worry about code. And also, this platform is like generally more suitable for the people who does not really know Flink, or like the data scientists who more prefer to write SQL query. Usually, people use it for the simple filter transformation or some simple aggregations. Of course, you can still write a very complex things in SQL. Well, here is a screenshot of the AthenaX platform. It's a very simple drag and draw UI that's designed for streaming applications using Flink SQL at Uber. It is deeply integrated with Uber's tech stack and also being carefully customized to simplify the user flow. AthenaX job usually consists of 3 components: a source connector, a SQL processor, and also a sync connector. So the source connector and the sync connector are usually configured through the configurations. There's no code needed. And for the SQL processor, it's just a UI allows user to write SQL queries. So this ways, like we are kind of abstract away all these underlying complications and also data format details from the end user. All they need to think is how to write the correct query. Well, internally, of course, we did a lot of work. So first of all, we have thousands of the Flink SQL job. We call it AthenaX job, running in production. And it all run on the same Flink job jar. The connector configuration and the SQL query are passed in as the configuration parameters. This approach reduces the maintenance overhead from ourselves. However, because Flink SQL only understands the raw data, which is like the Flink's internal format, the system needs to convert the source data into raw data and then transfer it into the format required by the sync. So, a most common use case, which is a Kafka source and Kafka sync with arrow encoded messages. The raw arrow bytes from Kafka needs to be converted into raw data. After run by the SQL processor, the raw data needs to be converted back into arrow for the output. So the schema registry play a very important role in this architecture. So schema registry will allow the use like the AthenaX job, the job inside the job to convert the arrow bytes into the arrow data. It also provides the arrow schemas so that inside the job it can be dynamically converted into the table schema. So our schema registry is developed in-house and serves as the source of truth for all analytical schemas. It is also a self-served platform. It provides all the backward and forward compatibility check, and validation will be performed during the schema change. Okay, we have gone through all the key components. Next, let's take a look at our motivations. We are talking about Protobuf today, but we cannot just avoid to compare the Protobuf with Arrow first, right? So there are many differences for these 2 different formats. Arrow is more self-describing, and the schema is in a JSON format. It's very easy to pass between different services to ensure the information needed to interpret the data correctly. Well, Protobuf is kind of different. It relies on the external defined proto files and use ProtoC compiler to generate the compiled Protobuf class and also the file descriptor for the service to use. So having the access to the generated class and the file descriptor is extremely important. And both Arrow and Protobuf support backward and forward compatibility, but it's slightly different. So for the arrow, the schema is travels through the schema. So it supports various of the changes, like adding field, removing field, promoting types. Well, some of this can be done on a Proto file as well, but the problem is Proto relies on the number to define how to decode the messages. And when you change the fields, the number of fields, and it might break the compatibility. But on the other hand, Protobuf is somehow more forgiving. Even if you supply the wrong schema, right, it can still decode the messages, but some of the fields might be missing, and it might lead to some data quality problems. Well, in terms of performance, there are many industry benchmarks. Protobuf is definitely faster compared to Arrow. But if you look at all these comparisons, Arrow is definitely a better fit for the data stack. Then why we are working on the Protobuf support? We do have a problem need to be solved, which is the data format discrepancy between our online microservices and the data stack. So Uber is built on thousands of microservices. And many of those microservices relied on gRPC Protobuf to communicate to each other. But when the data needs to go into the data stack, so it needs to be get into the Arrow format. So it's like two persons who speak different language. And then you need to have an interpreter to translate between each languages. So just a note here, Kafka itself does not enforce any format. So data can be stored at any format, like Protobuf, Arrow, or JSON. Also, the user of Flink Java application can still implement a Protobuf encoder and decoder by themselves. So the main problem is actually Flink SQL platform, AthenaX, and the other data platforms such as Pinot and ingestion. Okay, this is a real-world use case. So we have some online microservices. They actually write the Protobuf encoded messages into Kafka directly. Well, there are other services, they want to use those data, right? And they want to use it in the AthenaX platform. But AthenaX platform does not support Protobuf previously. We are all engineers. Well, there are tons of workarounds. Then another team comes in. They build a series of Flink Java application, the fast job, to convert the Protobuf data into Arrow data, store it in another Kafka topics for the downstream to use. So this customer conversion makes the assumption in the type compatibility. Also, well, this solution is built for this particular use case, right? And sometimes, let's say the Protobuf schema can get updated. Then someone needs to go to change the Flink job to make this particular data available in the Arrow counterparts. And then the problem is, people will not doing it very frequently. So the data from the Protobuf and Arrow sometimes get diverges. Well, this is additional storage cost because we store data in twice. But what's more important? Data freshness. Imagine you add additional layers between those flows, right? It will introduce additional latencies, which is bad for the real-time business. This has been complained by many, many users. So that's why we are thinking about just doing something more advanced or more natural, which is to provide native Protobuf support across our data stacks, including AthenaX platform. So we believe this is a good long-term option because, first of all, it aligns with Uber's strategy. gRPC Protobuf is one of the main protocols for service-to-service communication at Uber. It will continue to be this in a foreseeable future. Therefore, supporting Protobuf will benefit microservice users. Also, it offers better performance compared to Arrow, which is also very important for the real-time stack because it means lower latency, right? With Protobuf gets more and more popular in the industry, community also worked on Protobuf support, which we can leverage. So we don't need to build everything from scratch. OK, next, let's take a look at our architectures on how we solve this problem. Well, for the Java-based application FAST, this is relatively simple. We use monorepo at Uber for our Java services. And the Protobuf IDL can be easily synced into monorepo easily. So users only need to specify the payload class to be used for decoding the messages. Well, but one of the problems we notice is that Protobuf is still not yet a first-class citizen in Flink. So there's no schema evolution support for Flink yet. There is a open source Jira on this one, but it's not yet implemented. OK, but for the Flink SQL platform, AthenaX, the things become more complicated. Similar to how we convert Arrow records into raw data and convert it back into Arrow again, right? We need to do similar things for Protobuf. But the problem comes in now, because when you decode Protobuf, you need to have the generated Java class. You need to have the file descriptor set. And how are we going to solve this? First of all, there are a few options to convert the Protobuf into raw data. First one, Protobuf provides a more dynamic way to decode messages through a method called dynamic message, and also through the descriptor API. Well, there is a more commonly used way, which is use the Protobuf code gen. This is a solution which already supported in open source Flink. There's another more advanced and most efficient way, which is use the coded input and output string. But there are pros and cons for different solutions. For the dynamic message, well, this solution is very similar to how Arrow decode or encode messages. So it's really easy to maintain the conversion logic. But on the performance-wise, it's even slightly slower compared to Arrow. Well, and then the code gen solution, it provides a very good performance. But the maintainability and the stability is also supported by the community. But it requires the Protobuf jar, which we need to figure out how to get. The coded input-output string is the most efficient way, but there is no community support, so it's kind of hard to maintain. Yeah. So finally, by balancing between the usability and the performance, we still decide to go with the option 2. But it means we need to solve the jar access problem. OK, let's revisit this problem again. So all the AthenaX jobs are running on the same Flink job jar. The user can self-serve to onboard job at any time with any new schema. So it's impossible for us to pack all required Protobuf jar into the AthenaX job jar. The size of this job jar is going to get unmanageable. Well, you can say we can do something new, like we just modify the deployment flow and make each job build job jar independently and pack the jar together with the job, right? But it means we need to do a significant change in our deployment architecture. It will take a long time. With that in mind, we actually come up with a solution to dynamic fetch the Protobuf jars during the job bootstrap. We chosen to use Terabob, Uber's blob storage solution, underlying, it can be GCS, S3, HDFS. It doesn't matter, and we don't need to care about it. It supports caching, so we can use it to download the job jar fast and effectively. But to facilitate these downloads, the job needs to know where the jar located. It has a Protobuf URI. This will be stored in the schema registry. When a user registers the schema in the schema registry, we will run the Protobuf compiler to compile the jar and upload the jar into the Protobuf, and then store the jar location. Then all the way we will pass in this location to the Flink, to AthenaX job. Okay, we hook up everything together. But still, we need to run some benchmark to prove it's production ready. Quite interestingly, we do find some issues when testing our largest use case. There are two problems. First problem is we encounter a exceed the constant pool size limit error when we attempt to compile the generated code for a large schema. Well, this occurs. This is kind of like uncommon, but unfortunately, we do have a very, very big schema. The reason is being like the code split, logic split, too many split methods. So to address this, we made an improvement to only split the last code segment when size exceeds the limit threshold. Also, another problem here, current implementation checks the fail presence for types. And then after the Proto 3.15, the Protobuf itself introduced the fail presence check for non-permissive types, which lead to a significant performance degradations. Because, well, this large schema also have a lot of one-off fields. So we have to make an improvement to skip those fields. These two improvements already being merged into upstream by my colleague. Once we've done all these improvements, we run the benchmark again. Well, this time we get a much better result. So with the improvement, Protobuf is 4 times faster compared to Avro. It's almost 8.5 times faster compared to the version without improvements. Well, from a user's perspective, nothing changed. The data format is transparent for the user, and the platform automatically handled everything. So it's as simple as the past where they use the Avro-encoded messages. What we have get out of this project, first of all, as a great dev productivity wins, we are able to save a significant amount of engineer effort because users don't need to worry about writing a customer logic to convert the Protobuf data into Avro in order to be consumed in the data stack. We get good performance improvements, and users also get better data freshness. What is our key learning? First one, never skip benchmark. You will find surprises. The second one, the seamless user experience is important. Making the underlying data format agnostic to the end user improves the UI and the productivity. Users don't need to have additional learning curve for this new format. But what we are going to do next, there are quite a few things. So first of all, we have built the Protobuf support for the real-time flow. But we still have quite a few backfill use cases. We still need to support Protobuf in the backfill. We are working on the Flink injection project, which right now is still very Avro-focused. And we are going to expand the support for the Protobuf as well. Lastly, well, this is something I have not mentioned in the talk, but Protobuf has a very interesting type called any, So what happened to this type is the encoder, you can encode anything you want into this any type, and it requires the decoder to know what proto class it sends, and then use it to decode. So it's like, it's not well formatted, right? It does not have a type. Then if it is a microservice, you might write a logic to decode it properly. But as a platform, if we don't have the schema information, there's no way we can decode it. We're still working on a solution. But right now, the naive solution is somehow make any as a one-off. Yeah, that's everything I have.
On one of the last slides, you mentioned that you have some backfill use cases. I wonder how does it look like when it comes to data formats that you use?
OK, you are asking about the backfill use case, and you are wondering about how this looks like, right? So Uber's backfill stack is slightly different with the industry. We are doing the Kappa Plus architecture, where actually we read the Parquet file and convert it into the either the arrow object or the raw data, right? And for this one, talking about the AthenaX use case, right? What we can do is, well, right now we ingest data into the data lake as the Parquet form. Well, eventually stored as a Parquet format, and then we can convert the Parquet into the raw data directly. And for this Protobuf use case, actually the Protobuf doesn't involve in the flow. But the things becomes more complicated on the Java application mode, because we need to convert the Parquet back into the Protobuf object. We still don't have a good solution yet, but we do notice there is a Proto Parquet converter in the community, which we might be able to leverage.
Thank you very much for the talk.
I saw in your demo for the UI, you had one Kafka source and then the SQL. Does it support multiple input sources and joins as well for more complex queries, or is that not part of the Athena project?
It does support multiple input sources, but the output is just one.
If I understood this slide correctly, how do you, when you retrieve the Protobuf jar, you generate on the fly on the job manager?
The jar is being uploaded into Terabop during the schema registration. But when the job runs, right, it starts to fetch the jar from the Terabop and unwrap it to get a generated class.
Ah, I see. OK. Thanks.
Yeah.